this is by Professor Michael Otte. Michael is a assistant professor in the Aerospace Engineering department, and he has, I think, one of the more fun titles. So he's going to be talking about how to use many robots for fun and useful things. So I'm especially excited to see what Michael has to say.
Great, thank you for the introduction. Is the audio working?
Yes.
Okay, great. Well, we'll thank our lucky stars that that's happened. Thanks for the introduction. I'm going to share my screen. And yeah, this talk, it's kind of a two-part talk. So first we'll talk about the things that I think are fun, and all of it's fun. And then some things that maybe are a little bit more useful. So the first part is going to be about sailing a boat through a smart fluid composed of a robot swarm. And the second part of the talk will be using robot paths as event sensors. And this is collaborative work on both projects with different people. So I'll tell you kind of about the collaborators as we go through. So the first part of the talk is sailing a boat through a macroscopic smart fluid composed of a robot swarm. This is work with Paul Motter, Zachary Hoover, and myself at the University of Maryland. And here's the idea. We have a bunch of robots that are essentially particles in a smart fluid. And we have a boat that is inert, and the boat can talk to the fluid through its stern and bow transmitters. We're using Kilobot robots, which are a small robotic platform. I have one in my hand right here. And they are very small. They use vibration to locomote. They're very simple. They can send 9-byte messages to each other to kind of talk, and their communication radius is about 10 centimeters. So we run them on a little test bed, and the kilobots that are part of the boat, they're really just transmitters. They're not moving at all, but they're telling the rest of the robots what to do. So for example, for forward motion, the bow says, all the robots, please get away from me. And the stern says, all the robots, please come towards me, so that we have kind of a cycling effect that causes flow that pushes the boat. In order to turn motion, we have the particles orbit the boat. And we do this in a couple of different ways based on the type of a boat that we're talking about. The boat is kind of a teardrop shape here, which we found to help actually in the locomotion of the boat through the smart fluid. And so for the turning, we were interested in seeing, like, what are the effects of using a rudder, like a tail on the boat for helping to turn. So if we have no tail, then we need the flow to orbit the entire boat. So both the front and the back, the stern and the bow of the boat are saying, orbit in the same direction, which causes kind of a vortice that causes the boats to turn. And with the tail, then we actually have the particles orbit only the rudder kind of the stern transponder. And that causes kind of an overall moment of rotation on the boat, the way that they're interacting. And that causes the boat to turn. I guess I should mention that this work has appeared at the International Symposium on Robotics Research this year. So that's nice. That conference may still happen in person. The book proceedings are already out because of the funny things of 2020. But anyway, getting back to the talk here. So we tried 3 different boats. We had a no tail, we had a short tail, and we had a long tail. We ran them in a test bed, and we found that the short tail was better than no tail and also better than long tail, both for going straight and also turning, which was kind of unexpected for me, that even going straight, it kind of had better performance. One other thing that I should mention about the Kilobot robot is they have this light sensor on them, and we use that to basically teleoperate the transponders to say, try to go forward or try to turn or whatever. So we're using the light levels in the room to communicate with the boat to say, try to go forward, try to turn left, try to turn right. And then we navigate the boat along a Z-shaped path to kind of show that we can actually do something kind of interesting. So I am going to now pull up a video of this kind of working in a few cases. Let's make us full screen here. So anyway, these are just kind of the particles. Here's the transponders in the boat. And then here's the boat moving forward for a little while. And these videos, of course, are sped up because the kilobots move quite slow. But we have a bunch of them, which is very fun. And you can see the boat kind of moving from right to left. We did a number of repeated trials to see how far it could get you know, a certain amount of distance so that we could get mean and standard deviation over how long that would take. Here's, you know, more videos of the test. I'm probably going to skip through some of these videos. If anybody wants kind of to see these, I'm happy to share them later. But we also looked at rotation. So this is trying to rotate in a counterclockwise direction here. And you can see the robots are causing that to happen. So here is now going to be the Z-shaped test, and I'll just jump right to the showing 4 different trials of the Z-shaped test at the same time. And there's kind of 4 green dots that we've drawn on the whiteboard, and the human controlling the inert boat via the robot smart fluid is kind of waiting until the robot gets between one dot, and then we'll say, okay, turn to the right, and then, you know, drive straight until you hit the other dot, and then turn to the left, and then drive straight again. So the Z test is a nice test because it combines 3 different segments of forward motion with both a right turn and a left turn, so that we can kind of chain these maneuvers together. And I guess it's kind of up to the human to do it. So you can see in the upper left, we decided instead of having a left turn on the Z, the boat kind of got, you know, off course, so it ended up doing a turn in the other direction. So that is going to be the, oh, well, maybe we can wait. Let's see. The last one takes a little while to get there. Oh, it's so frustrating. Come on, you can do it. You can do it. Almost. Come on, there we go. Okay, and I think we called that close enough probably at some point. Touch the green dot. Okay, great. So yeah, I see in the questions right now, what are the real world applications uses of a boat in a swarm robot fluid? And that's a great question. But you know, this was a little bit more about the fun than the useful, I will completely admit. However, all work, I think, you know, the applications of this would be many years in the future, but there is a lot of interesting, some of my collaborators have also done interesting work on similar things in biological systems. So Aaron Becker, as well as many other, well, I shouldn't say many, but a handful of other people have done interesting experiments, some of which has involved feeding kind of magnetic material to little I don't even know the right biological word, but these little microscopic organisms that eat it, and then you can use magnets to kind of, they like to go forward, they have flagella that like make themselves go forward, but you can use magnets to help rotate which direction they go. The idea is basically manipulation of very small things. So this is a macroscopic smart fluid. You can imagine in maybe, you know, 100 years or maybe only 5, who knows how long it will take to get there. With miniaturization, you could have a lot of very small fluid particles that are a lot more like an actual fluid than this macroscopic thing. But you could use similar algorithms to what we're doing here to help manipulation of different objects, say for like small assembly tasks or something like that. So, you know, I think that there are interesting applications for this. I was more interested in doing it just because I thought that would be fun. So let's see, moving on to kind of the more useful half of the talk. So this is a different idea, different collaborators. This work is with Don Soft J at US Naval Research Lab. And this is about trying to collect information in the environment, kind of learning about the location of hazards and targets using a path as a sensor. So what do I mean by that? Well, we're motivated by a problem that we're looking for, like a lost sailor at sea, maybe a few lost sailors at sea. And there are also maybe some hazards in the environment that we would like to avoid, things that would like to prevent us from finding our lost sailors. And there's no communication allowed in the field in this problem. So we're going to send out our search and rescue vehicles to try to locate the targets. But if they happen to encounter the hazards, then there's a good chance that they will be destroyed. So there's also a chance that they might not be, right? We allow false positives and false negatives as far as the destruction goes. We also allow false positives and false negatives as far as the sensing the sailor if we happen to fly near them. But we also have like destruction, like a false positive destruction, right? Where the UAV is out there and it just gets struck by lightning or something like that, and who knows? So this doesn't necessarily mean that there was a hazard if it happens not to come back. But the idea is there are special places in the environment that are able to communicate. And we are going to send out our robots through the environment. We know where they're going. And then kind of if they are destroyed, if they don't come back, then that gives us information about the world. And it's noisy information about the world, but it's still information about the world. So let's say that path survival now is a sensor. So we get to determine the shape of the sensor by controlling the path that we're going to send the robots along. And that is kind of the whole key point of this talk, is that you can use path survival as a hazard sensor. Now, I'm going to say this is more general than just surviving a path. It's basically a binary sensor. Did some event occur along this path or not? And it's useful for cases where we can't really tell if the event occurred or not along that path until we kind of do some processing on whatever flew through there. So another example that I like to use is, let's say that we had a net and we were flying around looking for like some sort of insect that was hatching. And we come back and we look in the net to say, okay, did we get a bug or not along there? Some people have said, okay, well, you could just put a camera and see when you got the bug in the net, and that would give you more information. And that's true. So maybe we're looking for some form of biological agent that we have to test for in a lab once we get back. And all we know is kind of the path that the robot flew on. We do a test in the lab back there, and we know that it countered that biological agent somewhere along the path, but we have no idea where. So anyway, again, path as a sensor. So here's kind of how this works. We send out different UAVs along different, or robots, or what have you, along different paths, record whether or not they came back. And then after we have a few, there's kind of different things that we can say. So there's kind of two interesting points here after we've sent out 7 different robots into the environment, and a few of them have come back and a few of them haven't. So there's one place where it's kind of 2 successful traversals of 4 attempts. There's another place where there's 0 successes after 3 attempts. So even though there's kind of a high probability of hazard in one location based on this information, this other one where it's kind of, a 50-50 thing at this point, there's more information to be gained by trying to probe that area more. So we look now at the kind of Shannon information of this system, and we develop the kind of Bayesian update, and then the Shannon information theoretic kind of information entropy sort of gain that we can have for flying on a path. And this equation, is pretty standard stuff. You have your mutual information that you're gaining about the targets and the observations along the path. We have the probability of path survival, the mutual information of the hazards and the path sensor, and then some user preferences, right? Because we're looking for targets, we're also interested in the path sensor hazard detection. And so the user kind of says, how important is one versus the other? You can set that kind of however you want. And then you want to maybe, determine the best path to fly along to get the most information about these things. And then this kind of suggests a natural kind of sequential algorithm to fly, send out your robot, see if it comes back or not, and then update your map, and do this repeatedly to learn about where things exist. And kind of go through it. Here's kind of a quick example. So we have hazard belief in the top, we have target belief in the middle, and then we have the entropy of the hazards plus targets, equally weighted kind of entropy in both cases here. And the path is black if the robot survives, it's red if it did not survive. So you can see kind of how the hazard belief went up when the robot did not survive this particular path. And when we do get kind of successfully to the goal, then the target information is returned. So then we can update the target information. Here's kind of, this map. So we can kind of do that a whole bunch of times. This is just a toy example, but here's 15 different trials in sequence. And we can see that the hazards and the target kind of combined entropy is going down, which is a good thing. And also the hazard and target individually are kind of going down. But you can see that like the target entropy is stationary when a robot doesn't return, because we didn't get any information about targets. We did get information about hazards though, because the robot did not return. So it's not in this talk, but the entropy going lower corresponds to having better kind of true positive and true negative detection rates. If you have kind of some user-defined, 95% confidence that you're willing to call, yes, I think that there's actually something in the map at this case. So it correlates very nicely. This work appeared at the workshop for Algorithmic Foundations of Robotics in 2018, and it just appeared recently in IEEE transactions on the autonomous TACE. I forget. I apologize. I'm afraid that I'm going to butcher the name, so I'll just say IEEE TACE 21, which we're very happy about. So I think that brings us to the end, basically. This takeaways of this piece of work are that you can use a path as a sensor, which is pretty neat, I think, and that's also useful. So it's a very general method, and you don't have to plan to return the most amount of entropy possible. Any path, whether or not you get this binary observation, yes or no, along that path, can be used to update your map. So even if you're doing some other mission, you can record statistics on like, did we return or not, and locate hazards. We used a random walk and we're able to locate them as well. But if you're actively trying to maximize the information gain from your path, then you will more quickly kind of converge to where these things are existing in the map. And path-based sensor information gathering works. So another question, yes, we are assuming the hazards are stationary in this particular case. That is a huge assumption. Another huge assumption kind of in this, at Wafer, they have a dirty laundry slide. I took it out of this particular talk, but other dirty laundry, we are assuming that hazards and targets only affect sensors within their same cell. Anybody that's done any information theoretic planning knows that we are really, really making our life easy by doing that. There's also interesting stuff. If you check out the journal paper in particular, we have a kind of not optimal, but a very close to optimal algorithm that allows us to plan a lot more maneuvers into the future, because normally, right, like information gathering, especially if you're using Shannon information, it's a I'm forgetting the term of art right now. You have diminishing returns for the amount of reward that you can get, and that makes it very difficult to use like a focusing heuristic to make your life easier. So it's a sublinear, I'm blanking. Somebody that knows that.
Submodular?
What's that?
Submodular.
Submodular, yes, thank you. Submodular. Information is submodular. Can't believe I forgot that. Anyway, thank you for helping me there. Anyway, that's the end of my talk. Thanks for listening.
Awesome. Thanks a lot, Michael. This was a fun and a useful talk. There's a bunch of questions here. I think you addressed some of them. I'll maybe ask one of the lot, and maybe you can take a look after this. So there's someone who was asking, are the hazards assumed to always take destructive action if possible? So if there is a hazard, then will that always result in a destructive action?
No, we have kind of, no, the hazard has some kind of lethality rate, right? So that leads to both false positive, so that would lead to a false negative, essentially. We are assuming that the hazard is kind of invisible, so you can't fly over it and know that it was there. You could, of course, work that in. That would make the problem, slightly less fun from my point of view, because once you kind of see it, it's there, but easier to solve.
There's a comment that I'll read out because I think it's very interesting. As they're saying, I like how it connects to the smart fluid part of the talk. If, for example, if you had a leakage in a smart fluid container, you could learn where it is with the path-based sensor and then tell the robots to avoid that leakage zone. So I'm guessing someone is trying to connect the two pieces.
That would be interesting. Yeah. I mean, like, it's always really fun to try to find connections, and I haven't thought about that, but that would be. It could be a potentially very interesting connection. I would have to think about it more before I could say anything kind of intelligible about it. But I always like finding intersections of neat things. So that's a very cool question.
Awesome. So thank you again, Michael, for an excellent talk.
Thanks for having me.
So with that.